Welcome to day 24 of our 62-day low-level design course. Today we are going to delve into one of the most fascinating real-world systems, the elevator system. Over the next few slides, we will break down how an elevator system works from an engineering perspective. We will gain insights into system components, how to structure them using object-oriented design principles, and how to manage complex behaviors like concurrency and fault tolerance. This design challenge is a perfect opportunity to apply our knowledge of system design. Let's dive in and explore the fascinating world of elevator systems. Here's what we aim to achieve today. First, we will discuss the core components of an elevator system so we can understand how each piece fits in the whole. Then we will go over key design principles and best practices, including object-oriented programming and design patterns that are commonly used in the type of system. After that, we will explore the challenges of building a scalable, modular, and fault-tolerant system, an essential aspect of any robust software solution. Finally, we will conclude with practice exercises that will allow us to apply these concepts. So let's get started. Before we dive into the design, let's first understand the problem we are solving. Imagine a multi-floor building with multiple elevators. The goal is to design a system that can manage these elevators efficiently. We want the system to respond to internal requests and external requests. At the same time, the system needs to be responsive, efficient, and scalable. The elevator needs to handle user requests when someone presses the button on a floor or inside the elevator movement, deciding which elevator to assign the request to and moving it to the appropriate floor. Door management, opening and closing doors at the right time. Fault tolerance, if an elevator breaks down, it must be marked for maintenance and not assigned any requests. The system must be reliable, fault tolerant, and capable of handling concurrency, as multiple elevators will be running simultaneously. Let's look at the core components that we need to consider when designing this system. To track this problem, we need to break the system down into smaller, manageable components. Here are the key components in our design. Elevator controller. This class will manage multiple elevators in the building. It will track the state of each elevator and assign requests accordingly. Elevator. Each elevator will have its own instance of this class. It will represent an individual elevator's movement, status, and current request queue. Request. This class will represent a request from a floor or from inside an elevator. A request will contain the floor number, the direction, and the type. Door. This class will be responsible for the elevator doors. It will handle opening and closing actions when the elevator reaches a requested floor. Button. This will represent the internal and external buttons in the system. The external button is located on each floor and internal button is inside the elevator. Scheduler. The scheduler is responsible for deciding which elevator should pick up a request based on factors like current direction, load, and proximity. Display panel. This is a UI component inside each elevator showing the current floor and direction to the users. These components form the backbone of our system design. Now let's take a deeper look at each one and how it will function. Let's now dive deeper into the elevator class. The elevator has several key attributes. ID, a unique identifier for each elevator. Current floor, tracks the current floor of the elevator. Direction, indicates whether the elevator is moving up or down. Status, keeps track of the elevator's current state, whether it's ideal, moving, or under maintenance. Requests, this will be a list of requests that the elevator has queued up, such as picking up passengers from a certain floor. In terms of methods, we will have move, moves the elevator to a specific floor. Open door, opens the elevator doors when it reaches a requested floor. Accept request, adds a new request to the elevator's queue. The elevator class is central to our system as it represents the physical elevator and contains the logic to process requests and move between floors. Let's look at the elevator controller and the scheduler, which help manage the interaction between elevators. Now let's examine the elevator controller and scheduler. The elevator controller is responsible for managing the overall state of all elevators in the system. It will receive requests from users and pass these requests to the scheduler. The scheduler is crucial because it determines which elevator should handle each request. The scheduler uses an algorithm that takes into account the direction, current floor, and request queue of each elevator. It will assign the request to the elevator that is best suited to handle it. For instance, if an elevator is moving in the direction of the requested floor, it might be a good candidate to handle the request. This way, the system minimizes delays and optimizes resource usage. The scheduler helps ensure the system runs efficiently and effectively. When designing the system, there are several important considerations. Concurrency. Elevators should run in parallel, so each elevator should be on its own thread. This enables the system to handle multiple requests at once without delay. Prioritization. Elevators should prioritize requests based on their direction and proximity. If an elevator is moving in the opposite direction of the request, it can delay servicing that request. Scalability. As the building gets taller or more elevators are added, the system should scale efficiently. New elevators should be easy to integrate into the existing system. Fault tolerance. If an elevator goes out of service or a power failure occurs, the system should handle it gracefully by marking the elevator as unavailable and routing requests to other elevators. By addressing these considerations, we can build a robust and reliable system. Let's take a moment to think about some potential edge cases that our system might encounter. Elevator breakdown. If an elevator malfunctions, we think to mark it for maintenance and reroute requests to the other elevators. Power failure. In the event of a power outage, we will need a strategy for the elevators to return the nearest floor and their loads. Overload elevator. If an elevator exceeds its weight limit, it should stop operating until the load decreases, either by passengers leaving or by being unloaded manually. Handling these edge cases is crucial to making sure our system is resilient and does not fail unexpectedly under challenging conditions. In building this elevator system, we will leverage several well-established design patterns. Singleton. The elevator controller should follow the singleton pattern to ensure only one instance of the controller exists at any given time. Observer. The button class will use the observer pattern. When a button is pressed, it sends an update to the elevator controller, which then decides how to respond. State. The elevator will use the state pattern to manage its different operational states like ideal, moving, or under maintenance. Strategy. The scheduler can utilize the strategy pattern to choose between different scheduling algorithms based on the system's load and or specific rules for handling requests. By applying these design patterns, we ensure our system is modular, maintainable, and easy to extend. Here are some best practices to keep in mind while designing this system. Single responsibility principle. Each class should have only one reason to change, which means each component like the elevator, scheduler, and button should only be responsible for its specific task. High cohesion, low coupling. Keep related functionalities within the same class and minimize the dependencies between different classes. Exception handling. Always design for graceful failure. If something goes wrong, the system should remain functional and the user should be informed appropriately. Testability. Design your classes in a way that makes them easy to unit test so you can ensure the reliability of your system. To summarize, we have gone through the process of designing a low-level elevator system. We have broken the system into modular components, applied object-oriented design principles, and used design patterns to ensure scalability, maintainability, and reliability. This approach allows us to build a system that can handle real-world complexity and edge cases while also remaining efficient and robust. For homework, I want you to extend this design by introducing a feature where certain VIP floors can get immediate access to elevators regardless of the current requests. Additionally, simulate the elevator system using multi-threading so that multiple requests can be handled simultaneously. This will give you hands-on experience with concurrency and simulation design. That wraps up today's session on low-level design of an elevator system. I hope you now have a deeper understanding of how complex systems like this can be designed using object-oriented principles, design patterns, and best practices. Remember, this is just the beginning. You will build on this knowledge as we continue to explore more systems in the next sessions. Take some time to work on your homework exercises. I will see you in the next, and thank you for your attention.